First of all, let me thank Shubro for inviting me to this fantastic place. This is my first time in India. I'm having a great time. And thank you very much also to the organizers of the conference for giving me this opportunity to tell you about our recent work. So the work I'm going to present is done by these two young, talented scientists, Li Kunshi, who's a postdoc in my group in Leipzig, and Oles, who used to be my PhD student when I was in PKS, and has moved as a postdoc now with Justin in Singapore. And so basically, the question we're trying to address is, how should we fill Floquet bands when they are coupled to heat baths? In particular, what is the nature of or what is the analog of a Fermi liquid state in a Floquet band? Okay, so I'm now in Leipzig, so just a little bit of advertising at the University of Leipzig. It's a place with very long history, where Heisenberg used to be a professor, and during his golden years, so he trained the guys who put the pillars of the foundations of solid state physics as his PhD students there in Leipzig. Very close to Berlin and Dresden, about an hour. So if you're ever around the area, please let me know. It would be great to have you visit. All right, so here is a summary of the main ideas that I want to communicate, okay? So the question is, how should fermions fill a Floquet band? And there are going to be two settings in which we are going to look at this question. So first is, how should they fill the band when they are coupled to a fermionic bath, okay? And so the answer is that when fermions are coupled to a fermionic bath and they are filling a Floquet band, they will not occupy this band according to the Fermi-Dirac distribution, but instead they will occupy it according to something we call the Fermi-Dirac staircase, okay? So it's like a version of a Fermi-Dirac distribution, but you have many steps, okay? Many steps of the Fermi energy shifted by the driving Floquet frequency, okay? And as a consequence, then when the bath is at very low temperatures, these steps are going to become sharp jumps, okay? And so, in a sense, you have a situation in which you have many Fermi surfaces, okay? At every one of these jumps, you're going to get a Fermi surface. You have a situation in which you will have several sort of mutually enclosed Floquet Fermi surfaces. And so this state is the state we call the Floquet Fermi liquid, okay? And
so this is effectively zero temperature.
That being sharp is zero temperature, and if you make it finite, then it smears just like the usual Fermi liquid for fermionic baths. But I'll say something more non-trivial in a second about bosonic baths. And so this Floquet Fermi liquid, allows to understand very interesting phenomena. So I will show you how, by thinking about this carefully, we can solve an old problem in optoelectronics. So I will show you that it's actually possible that when you shine light with frequency within the optical gap of a metal, to have, even though you have vanishingly small light absorption, you're in the optical transparency region of the metal, it's actually possible to have photocurrent. So you can have a DC net rectified current, and this was a long-standing confusion in optoelectronics that I think we have finally solved, okay? But there is various other manifestations that are more direct. So you can see these various Floquet Fermi surfaces, for example, by applying a magnetic field. And because you have multiple Fermi surfaces, you're going to get quantum oscillations, but now with some additional frequencies associated with these different areas. So you get some beating pattern of the amplitude of Shubnikov de Haas. But this part is unpublished, okay? So this part is really cool. I'm very excited about this. All right. So we have now looked at the problem of how the Floquet band is filled when the fermions are coupled to a bosonic bath as well. Okay. And here is what we found. Okay. So when the bath is at 0 temperature, there are still some sharp singularities in the occupation of the band.
Can I ask one?
Sure.
In the Fermion, but the exchange particle with the
Yeah, I'm giving you the, this is the menu, okay? So I'm gonna go into each of them into detail. So if it's not clear how the setting is, this is just to get you excited, okay? So this is just the punchlines. So what happens with the bosonic bath is there are still non-analyticities in the occupation, some kind of cusps, but there are no jumps of the occupation. So there is no quasi-particle residue, in a sense. So this is why we call it a non-Fermi liquid. It's a Floquet non-Fermi liquid. So there are sharp Floquet Fermi surfaces, but they don't have jumps, they don't have residues. But the most amazing thing is that even when the bosonic bath is at finite temperature, these non-analyticities remain perfectly sharp, just as sharp as they were at 0 temperature. So this is why we want to call it ultra-critical or ultra-quantum critical. Okay, so it's a bit of a mouthful, the name, all right? It's a ultra-quantum critical Floquet non-Fermi liquid, okay? But it's very strange state, okay? So it remains, the Fermi surface remains sharp, even at finite temperature. So the system has still power law correlations, like in the Friedel oscillations. There are sharp, perfectly sharp Fermi surfaces at finite temperature, which is something that has no analog in equilibrium, okay? So now let's set up this more concretely, right? That's kind of the overview of the main messages. So let's imagine, we have a Hamiltonian that depends on some parameter that is time dependent. And so, we know when this parameter is, held constant in time, we know how to, using the principles of statistical physics, how to write down an ensemble, okay, for this situation. We just go to, equilibrium, maximize entropy. But in general, when we are driving the system in time, when we're changing the parameter as a function of time, we don't have general principles to, write down ensembles. The problem becomes hard, but also kind of the message of this story that I'm saying in part is that, it's also a very rich problem. And there is a lot of quantum states, I think, in non-equilibrium steady states, okay, of driven systems that we still are, far from understanding, right? And so one important consideration is that if the system is perfectly closed, if it's described just by a Hamiltonian and you're just driving it in time, then basically the second law of thermodynamics tells you that you are going to keep heating the system up, increasing the entropy continuously if you keep pumping it, okay? And there is no interesting late time steady state, modulo the discussions, the very subtle discussions that you guys are going to have in this conference about possibility of time crystals, etc. So, but generically, there is going to be no late time interesting state. It's just going to be, don't drag me to the subtle stuff yet. Okay. I should learn about this. It's something I don't know, so definitely we'll try to catch you to learn about this. So, but I don't want to be in this setting in which the system is closed because of those kind of limitations. So I want to be in a setting in which we are driving the system, but the system is also coupled to a heat bath, okay? And this will allow us to have non-trivial steady states in which the system just doesn't heat up to infinite temperature, okay? So that's going to be the setting. We're doing work on the system, and the system is releasing that energy into the bath in the form of heat. So there is a finite, at late times, a well-defined steady state, unique, but with some energy density that is still not super high. And so that the system is still doing something quantum and non-interesting, and interesting. Here is one of the key messages of this talk, all right? There is a crucial difference between equilibrium and non-equilibrium physics. So when you're driving and you're coupling to a bath. So in equilibrium physics, whatever bath you couple your system to, this might be fermions, let's say this one is bosons. If this bath is very large compared to your system and the system bath coupling is very weak, If you open the textbook, it doesn't matter what you're coupling into. You always get the same ensemble under these conditions in which this that I just mentioned. Okay, so there is a tremendous universality in equilibrium in which the bath does not matter. And that's not true out of equilibrium. So that's one of the key messages. When you're driving a system and you couple it to two different baths, even if those baths satisfied all the conditions that would have made the system have the same equilibrium ensemble, you might have two different steady state ensembles when you're coupling to the bath, even in the limit in which the coupling to the bath goes to zero. Okay? Even in the super weak coupling limit, if you couple to fermions versus both bosons, the steady state ensemble can be very different. That's going to be one of the key messages. So let's talk about fermions first. Okay, the fermionic setting is nice because you can solve everything exactly. Okay, so here we imagine, we have a Fermi system. Okay, just to be concrete, just imagine you have some kind of tight binding model. The blue sides are the system of interest. And then there is other sides that you just call bath sides, okay? But the whole thing as a whole is just a non-interacting fermion tight binding model.
Are you speaking the memory less?
Just 1 second, just 1 second. Let me set it up and it's exact. It's exact, no approximation. The fermion can be done exact. So the fermions can tunnel to the sides with some tunnel amplitudes T prime. Let's imagine. And because it's everything is non-interacting, then the Hilbert space of a single particle decomposes into a direct sum, okay, which is useful. So you can write down the wave function in a block form, a system part and bath part, the wave function of a particle moving in these dots, let's say. And so just by doing sort of very simple integration of the equation of motion, you can rewrite the equation of motion for the system wave function without having to make any reference to the bath wave function. So this is completely exact rewriting of Schrödinger wave function, or Schrödinger equation, sorry. So it has the part that is just the Schrödinger equation for the system. It has a part that contains the propagator inside of the bath, and the HBS is the off-diagonal part that is taking you to the bath, so basically the tunneling. But you see, it's acting on system wave function. And this contains all the memory and decay. It's non-local, it's an integral differential. So memory, decay, and renormalization of energies is basically contained here. But crucially, it also is also an inhomogeneous equation. So it does not become zero when you make the system wave function equal to zero, but it contains a source term that knows about the initial condition of the bath at some distant time, T naught, some distant past. But it's an exact equation. And this balance between this decay, this is basically what gives you decay, and this source term that acts as a feedback, these two things balance so that in the end you can have non-trivial late time solutions of a wave function in which the wave function doesn't just completely leak into the bath and completely decay, okay? Now, by making some assumptions about the bath, so we can call it featureless ideal bath. So we're going to imagine that the bath is just a collection of sites with some energy levels that have a spectrum that is very broad compared to the system spectrum. It's flat and perfectly broad. It's just a bunch of random local energy levels to which you're tunneling. So under those conditions, in the limit in which this energy spectrum becomes very broad, you can show that Schrödinger equation just becomes very simple. Okay, so it's the usual Schrödinger equation plus an imaginary part that you can compute explicitly is given by the density of states of the bath times the tunneling strength, okay, plus this source term. So this is an equation that maybe people use, for example, when they are doing open quantum systems. But one piece that is usually ignored is this source term. Okay, so it's important to keep this source term that contains the initial condition of the bath at some initial time. And so basically the problem becomes, if we take some initial condition for the bath, let's say at initial time the bath was in the thermal state, the Fermi-Dirac distribution with some temperature, we just need to take every one of the states in this ensemble evolved according to this equation, and that way we can find the late time steady state, all right? And one can do this exactly. So this box is a solution of the late time one body density matrix of the system for any system Hamiltonian. So it could be Floquet or non-Floquet. This integral gives you an exact solution, assuming that the bath is in the Fermi-Dirac, state, okay? So this is even when the bath and system have a finite coupling. So, and when you take the system bath coupling to 0, it becomes very weak, so that it's an ideal bath. And also you make the assumption that the system is a driven Floquet system, so with a periodic Hamiltonian, and you decompose the wave functions in Floquet, harmonics. Then you can prove that this expression for the late time steady state of the system is given by this very nice simple form. So this form is actually a special ensemble of the a special case of the periodic Gibbs ensemble that was introduced in this reference, okay? But with the weights fixed, okay? So the weights are kind of filled and uniquely determined by the bath, the occupations of the states in the Floquet ensemble. And so let me kind of walk you through this formula, which is essentially the main result of this fermionic part. So for every Floquet state, with some label A, that Floquet state will have some Floquet energy, okay? And the occupation is going to be a weighted sum of Fermi-Dirac distributions shifted by the Floquet harmonic. So here capital omega, sorry, sometimes I flick capital omega and little omega. This is just the driving frequency. So it's a weighted sum of shifted Fermi-Dirac distributions where you're kind of shifting the chemical potential by the driving frequency, and the weights are the squares of the Floquet wave functions. Sorry. And so you get this kind of picture. You get a bunch of steps for occupying the different Floquet energies, okay? And this is basically what gives rise to this staircase, okay? Staircase occupation of the Floquet states. So in a sense, you can picture that it's as if you had the Floquet energy, and now consider the boosted copies of that Floquet energy by the driving frequency, and you imagine that there is a global chemical potential which is fixed by the bath, and so that's where you get the different jumps, in a sense. Every time the chemical potential intersects one of these Floquet copies, you're getting one of the jumps of this staircase, okay? That's kind of the picture of what is the state. So, but
What A stands for?
A is just a label for different Floquet states. Here, I'm still not even talking about bands, just some label for the eigenstates. Yeah, so we can use this kind of general formula for a Floquet block band. So now imagine, for simplicity, I have like the simplest ever band. So it's like just one state per unit cell, no Berry phases, and we're just doing pile substitution for some electric field that is driving you. Some monochromatic electric field with some frequency omega. So the only thing that you're doing is really shaking the crystal momenta with this vector potential. So by using this formula that I described, we can then obtain what is the ideal occupation of this Floquet band when the system is coupled to a fermionic bath, and we get this Floquet Fermi liquid that I was mentioned at the beginning. Okay, so it's a bunch of Fermi-Dirac distributions with some weights that are the squares of the Floquet wave functions. So it's determined by the Floquet problem. So let me tell you then why. So that's the state. So by the way, just to kind of, in this notation, K is the canonical crystal momentum. So it's not the gauge invariant crystal momentum. So the picture is, you should imagine basically that there is this staircase-like occupation of the states, but the physical momentum is oscillating back and forth, okay? So electrons are kind of moving because you're driving them by an electric field, but their kind of internal, state of occupation has a non-trivial staircase-like structure, but the physical momentum is going back and forth. They're being shaken by the electric field, right? And so let's try to understand how this state can have current, rectified current, electric current, this steady state, okay? So the key really for why there is current is that in the Floquet setting, the occupation of a state, of a Floquet state, is not a function of the Floquet energy alone. So in equilibrium, the occupation of two states only knows about their energy. It does not know about its wave function. It's quite robust in equilibrium. So two states that have exactly the same energy could have very different wave functions, and they would have the same occupation in equilibrium. In Floquet, because of these weights, you can have two states that have exactly the same Floquet energy in the Floquet band, but they will have different occupations in the steady state, because the steady state occupation also knows about this Floquet wave function, okay? And that's really the key to explain why there can be rectified current in this steady state. So, the time average current, so, the current is just, whatever is the occupation times the group velocity of the particles. Let me average over one period this expression. And so you can show in the end that this average of the energy for this one band model equals the Floquet energy, actually. So you get in the end a very, an expression that resembles a lot what you have in equilibrium. So the DC rectified current is this occupation times the group velocity that you would compute from the Floquet energy. But the key again, if this function was only a function of the Floquet energy, this thing would be a total derivative. So when you integrate over the Brillouin zone, there is no way to get current in equilibrium. But in the Floquet setting, because of this ingredient that I told you, that the occupation is not a function of the energy alone, this is not a total derivative. And so in general, you can have rectified current, okay? So this is how to understand why you can have net rectified current. And this solves a long-standing confusion in optoelectronics that goes back to this paper that, they said that in the steady state, if you're shining light in the transparency region of a metal, there will not be photocurrent. And actually, the mistake of their analysis in modern language was that they assumed that in the steady state, you would be occupying the Floquet states according to the Fermi-Dirac distribution. That was precisely their issue. But if you take into account this non-trivial point that I made, then there is no issue, and there should be photocurrent inside of the gap, of the optical gap. Okay, you can see this, multiple Floquet Fermi surfaces by quantum oscillation. So if you apply magnetic fields, you see beating patterns of the oscillations. I don't want to go too much into details because I'm short on time, but basically this is a way, I believe, to essentially understand this phenomenon of microwave induced resistance oscillations that has been seen in two decks of gallium arsenide since a long time ago from a Floquet point of view. So what I'm trying to say basically is that these additional oscillations of Shubnikov-de-Haas that people see when they shine microwaves on two decks are essentially just these quantum oscillations of these extra Floquet Fermi surfaces. So this phenomenon, in a sense, has been seen when it's kind of, but it has not been interpreted, at least in this language. There is various things that are interesting, but I'm short on time, so let me jump to bosons, which are even more non-trivial. So let's now, go back to the same question, but let's now replace, instead of the fermions being able to tunnel in and out of the system, let me replace the bath by a bosonic bath. And I'm going to take like a very simple sort of caldera-legged style bosonic bath in which you have a bunch of local harmonic oscillators with some spectral distribution of their frequencies and some very simple on-site density coupling of those oscillators to the fermions, okay? But the fermions cannot go out. They just interact with these harmonic oscillators, okay? And so we, derive very carefully a Boltzmann equation for this. I really recommend this book if you guys are interested in learning these things. If you want to derive like hardcore Boltzmann equations, very microscopically, very detailed, this book is great. So, it has the usual part that is the, non-dissipative part and the collisions. But in the book, you can find very clear expressions for collision in any kind of setting. So this is the evolution operator of the system. Chi is the coupling between system and the bosons. And so you can adapt it to your problem of interest. And we took that sort of full microscopic Boltzmann equation and we showed that in the limit of weak coupling to the bath, so chi here is the strength of coupling to the boson modes, the solutions of this Boltzmann equation, of this full Boltzmann equation, become time independent in the crystal momentum basis. So it's the same kind of setting that I was just telling you. So in the steady state, the system eventually thermalizes, reaches a steady state in which there is a kind of rigid occupation when you're moving in the frame, in the crystal momentum frame. The physical momentum is always K minus A, so they are oscillating, but when you track the electrons in this sort of moving frame, the relative occupation is static. Okay, you can prove that in this weak coupling limit. And so the problem becomes a problem of solving a Boltzmann equation as if it was static. And all the Floquet information, it's absorbed or encoded into these transition rates. So this is kind of looks like the same Boltzmann equation you would solve in equilibrium, but the key is that these W's are very non-trivial and they contain all the Floquet information, okay? But the problem that we did is just to solve numerically this Boltzmann equation in detail. So let me kind of flash what these transition rates are. So they decompose into two kinds of terms: emission of quanta into the bath and absorption of bosonic quanta from the bath to have electronic transitions. So the emission terms have the following character. So the electron kind of comes from a Floquet state and can go into another Floquet state. They might have different Floquet energies. And the boson now, because you're driving it in an emission process, does not have to satisfy energy conservation with the Floquet energies, but instead there can be various kinds of emission processes labeled by an integer here, L, in which the boson energy differs from this difference of Floquet energies by multiples of the driving frequency. And the transition also depends on the Floquet amplitudes as before. So this conclusion that you would have rectification inside of the gap is also true here, because all the occupations will not be functions only of Floquet energies. They will also depend on Floquet amplitude. So there's a kind of matrix element of overlap of the initial and final Floquet state. And there is a factor that contains the information about the coupling of the bath, the density of states of the bath, and the temperature of the bath. So the Bose occupation of the modes, of the bosonic modes of the bath. Okay, these kind of equations have also been derived by a few other people in the literature. So we take this very kind of serious Boltzmann equation and we just put it in the computer. This, we cannot do analytics. And these are the solutions, okay? So initially, let me take, just a simple kind of parabolic band. And it's important in this part of the story, what is the density of states. So I'm gonna first consider a case in which the bosonic bath is gapped. So it has a gap delta, and then it's just flat. The density of states of modes of the harmonic oscillators. 5 minutes, very good. And so initially, when you have very weak drive, you have some kind of thermal distribution, right? So the electrons are kind of, even though the bath is at 0 temperature and you're shaking the electron temperature is a bit higher than the bath. So it's initially kind of a broadened Fermi-Dirac distribution of the electrons, but then as we sort of increase the amplitude, we notice that some kinks started to appear, okay? Thank you. So, and then, the kinks are always there, but then they become more visible when you increase the amplitude. So here is an example in 1D in which the bath is at 0 temperature. So there's a kink in the occupation where the non-analyticity scales as a square root away from the kink. In 2 dimensions, the kinks are a little bit weaker, so they are jumps of the derivative. There is a discontinuity of the derivative of the jump where the kink is located. This is for a bath at 0 temperature and with this kind of density of states. If the bath is ohmic, so if it has linear density of states, the kinks are still there, but they are a bit weaker. So before we had square root, here now is like a jump of derivative in 1D, and in higher dimensions in 2D, the kink becomes a jump of the second derivative. So the point is there is always a kind of non-analyticity. It's stronger when the bath has a jump in the density of states. But there is always some very sharp non-analyticity. And the amazing thing is that the non-analyticity survives at finite temperature. It does not smear out by temperature. In fact, another kink appears at finite temperature. We understand one kink is dominated by the emission processes, emission of quanta into the bath, and the other is dominated by absorption processes. So the absorption peak kink turns on at finite temperature. But the strength of the kink is not, smeared out. It's still there, and it just kind of dies out smoothly as you increase the temperature of the bath. The absorption is even non-monotonic, eventually dies out. And the way to understand where the kinks are appearing and how they are appearing is a bit as follows, okay? So in equilibrium, if I start at the bottom of the band, and let's say the bath is at 0 temperature, there is nowhere I can go because I can only emit photons or bosons, but those have finite energy. So if I am already at the bottom of the band, I cannot go any lower, right? But in non-equilibrium setting, there are new channels that open up for scattering. And even if you're at the bottom of the band, at the bottom of the Floquet band, you can scatter to other points in the Floquet band by using this property that I mentioned, that the boson energy doesn't have to match the energy of the difference of Floquet energies, but it can differ by an integer. Okay, so even if you start with 0 energy at the bottom of the band, you can lower the energy, so to say, lower the Floquet energy by making this L equals -1, so that this is compensated by a plus omega. So in non-equilibrium setting, you can further lower the energy even if you're at the bottom of the band. And so this opens up a set of transitions that connects only 2 regions in momentum space. So those that are connected to the bottom of the band by emission, and those that are disconnected. And these kinks appear at the boundary of those 2 regions. That's how these Floquet Fermi surfaces appear. But the amazing thing is they are there at finite temperature. They are sharp, so these Fermi surfaces are sharp at finite temperature. So if you look at things like 2-point correlation functions, which in a usual Fermi fluid, they will have oscillations basically reflecting the kind of Friedel oscillations, but an overall power law envelope. Now you have also these power laws of the decay of the Friedel oscillations essentially for these non-Fermi liquids with different powers from the ones that you have in equilibrium, because the singularities are not jumps, they are different, but surviving at finite temperature. All of these Friedel oscillations of a Fermi liquid are cut off by a correlation length that is finite at finite temperature. The Fermi liquid is only critical at 0 temperature. And at any finite temperature, the Fermi liquid is at sufficiently long distances behaving like a classical gas. But this system is not. It has a sharp Fermi surface even at finite temperature, and it will have power law Friedel-like oscillations even at finite temperature. So how is it that you can, even though the temperature of the bath can be larger than Fermi energy, and even though the temperature of the bath can be larger than this driving energy, how is it that you can remain quantum? There is a parameter that remains quantum, which is the amount of work per cycle that you're doing in the Floquet problem. This amount of work per cycle is basically given by this combination, velocity times electric field divided by omega. That's the typical amplitude of the amount of energy that you supply to the electrons by the work. And that remains always much smaller than h bar omega. If you want to go to the regime in which this inequality is inverted, you would be in the regime in which you have a lot of Floquet, very small frequencies, so a lot of Floquet bands very closely spaced. So what I'm trying to say is to go to the classical limit, if I am at high temperatures and I solve the classical Boltzmann equation of fermions coupled to a bunch of harmonic oscillators, I should recover some kind of behavior of whatever classical fermions are doing. So in order to go to that limit, you have to do something highly non-perturbative in Floquet space so that you invert this inequality. So the connection to classical physics is very non-perturbative. And this is how these systems can remain quantum, even when they are very hot. It might be possible to realize this experimentally, but since there are no experimentalists, I assume in this audience, let me skip this. Only if anybody has a friend that can do microwaves, experimental friend, please tell me. But I believe this can be realized experimentally. So with that, let me just leave this slide, which basically contains the summary of the main ideas. And thank you for your attention. The key physics is that the boson, the fermion bath, the fermions can
exchange particles.
Exchange. And
Exchange of energy.
this way, the fermion bath, in a sense, he fixes the chemical potential. There is a kind of notion of chemical potential, even still out of equilibrium, which is the one that allows me to kind of draw this cartoon, you see? There is a kind of chemical potential intersecting all the Floquet bands. In bosons, there is no chemical potential. So there is no way in which I can kind of draw this type of cartoon that I would draw for
Second
fermions.
question would be that you are still doing in Markov regime, right? Mostly in memory-less case.
In the, no. So in the Boltzmann equation that I used, and this is maybe something I was too fast, but I tried to emphasize a little bit. This Boltzmann equation is a non-Markovian Boltzmann equation. It has memory, you see? And my statement is that even with this kind of very sophisticated Boltzmann equation, in the limit of very small coupling to the bath, okay, you can prove that the steady state behaves in this way, as if it was non-time dependent. The only time dependence is this kind of motion of the crystal, the physical momentum back and forth by the Peierls substitution.
But for fermions, you are taking...
For fermions, it's even safer because you can solve it completely exactly at finite coupling to the bath.
Okay, one question at the back.
The kinks that you observe depends on the strength of coupling to the bosonic path?
Yeah, the strength of the kink is always there at finite coupling.
Yes.
But the stronger you make it, the more visible, the more sharp it becomes and the more pronounced it becomes.
And the different colors in your graph denotes different temperature of the bath.
Which one? This one?
Yeah.
This one, yes. Thank you for the question. Yeah, that's actually temperature. I didn't emphasize it. So this one is zero temperature of the bath, and the bath temperature here is increasing as the colors go up.
Okay, thank you.
Yeah.
Okay, yeah, one more questions. Yeah, sure.
Yeah, I wanted to ask about the fermionic bath. So you show only three kind of jumps. So there are
many.
And it's related to the Magnus expansion. Like, can I say that the strength of the jumps tell us how strong the Magnus expansion jumps are or something?
Yes, so the strength of the jumps is, perturbatively, for example, the first non-trivial jumps have this scaling with electric field. So the lower the frequency, which is when the Magnus expansion is less controlled, then the larger these ones become, these non-trivial jumps. They have this type of scaling. Yeah.
Yeah, so we'll take one from there and one from here.
Yeah. So the staircase result, does that generalize to two frequency drives, for example? Do you get staircases at n1 omega 1 plus n2 omega 2? Have you looked at that?
No. We haven't looked at that. If they are not sort of commensurate, so there is a global frequency.
Yeah.
We haven't looked. So that's a good question.
Okay, Devanjan.
Just a basic question. Maybe it was implicit in what you said, but can you make a sharp statement about like some Luttinger's type theorem for your Floquet Fermi or non-Fermi liquids?
Yeah.
You talked about quantum oscillations. So what sets the size?
Yeah, I don't have any kind of very good, sharp kind of Luttinger theorem. That's a good question. But just to kind of give you a sense, so this you can picture these other jumps as being like quasi-particle residues, as if you had a multi-band system, right? But the other bands have some quasi-particle residue that is not one. So where maybe a good cartoon. You see, each of these weights, the jumps, So when the amplitude of the drive goes to 0, then the main jump goes to 1, and all of these secondary weights go to 0. So it is as if you had a multi-band system, but with different weights of the other fermions. So it basically, that controls how strong is the amplitude of the contribution to the Shubnikov of the Haas.
Right, but Luttinger's theorem makes no reference to the
Sure.
recipe itself. So
Yeah. So I say quickly, I don't know any very good sort of Luttinger theorem, and this is just to also illustrate, how tricky it is. These weights all add up to 1 in a given k, but once you start adding them at different k's and so on, I don't know how to make anything very smart about that.
Okay, so maybe we should move on, and thanks for a very nice talk.
Thank you.
So let's just thank the speaker.